Hello, everybody. Hope everybody's awake after this big, wonderful lunch. So I'll be speaking about this memory-efficient sanitization technique. This is a joint work with my co-authors within Data Domain, Shilane, Nitin, Garg, Windsor, and I need to thank them and as well as the Data Domain engineers that have gave us a lot of feedback on this. So basically, the very first thing that we want to understand is what sanitization is all about, right? So you have, in some cases, some classified information that you have classified storing for it, and we are storing that data in the classified storage, and by an accident, that classified data can land on an unclassified storage, and we call that classified message incident. So the way we define sanitization is that we want to restore the storage system to the point as if the classified message incident has never happened to that storage. So we also need to consider some threat models before we actually address the problem that we want to address. So we have, basically there are some predefined in the literature, some threat models that we are reusing, which are casual attacks, robust keyboard attacks, and laboratory attacks. So the casual attacks is when someone tries to get access to the file system through normal interface like NFS, CIFS. A robust attack is when someone is trying to get access to the system and tries to read the unallocated blocks or even the direct blocks from disk. And laboratory attacks are more sophisticated techniques that try to use specialized hardware to try to detect what the prior state of the disks or the magnetic states or the magnetic values were, even after you overwrite those values. There has been guidelines on how to do sanitization, and if you want to have a storage that complies with those, you need to follow them. So basically, if I summarize them, we can summarize them in two levels. The first one is the clearing level, where they recommend to overwrite the storage at least once. And you can overwrite with any pattern, zeros, ones, random pattern. And then the purging level, where you basically want to degauss your disks or destroy your disks. So those are the two extremes. In the paper, we describe how we comply with both of them, but in summary, we basically sanitize the data first, and then we try to move the data after the duplication to another storage. And then if you want to comply with the purging level, you can either degauss the source disks or destroy them. You can find more details in the paper. So one question that comes up when you talk about sanitization is why not cryptosanitization? So there are a few reasons for that. So the very first one is how do we define it is encrypt each file with a different key, and then if you need to sanitize that file, you throw away the key. So the duplication introduced some challenge in this scenario because blocks are shared, or not only the duplication, but also snapshots. Key management is a huge hassle in this scenario. The NIST and DoD guidelines, they do not accept encryption as a way of doing sanitization. And then the most critical one for us is you sacrifice performance of file system operations like read-writes, replication, because of sanitization, which is supposed to be relatively rare as compared to those operations. And sanitizing a storage system is slightly different. It's considerably different than sanitizing a device. If you have a device and you want to sanitize it, you just go and overwrite the blocks in that device. You can use any application for that. But if you have a storage system, you have data there, and you don't want to go and destroy your system to sanitize it, so you need to take care of that. And there are systems that do in-place overwrites. So in that case, you can just try to follow the metadata if the blocks are not shared, identify the unique blocks, and overwrite them. But the duplicate systems, usually they are log structured, and because they are log structured, they have big units of writes, and those writes are, the blocks are not usually overwritten. And then you fragment those blocks over time. And because of that, you need to somehow copy the data from the fragment blocks into new blocks and then erase the free blocks in the system or the affected areas by the incident. In this paper, we describe a technique that we do bulk sanitization. And bulk sanitization meaning that you delete all the files that are affected by your incident and then you run this feature. And that will run on the entire system. In the duplicated systems, sanitizing individual files is very challenging because you need to track all the unique blocks associated to a file. And not only that, what if the file has already been deleted from your storage system? So you might have those incidents where you have already deleted the file and you still want to sanitize the system. So we have a few requirements for sanitization. Basically, we want all deleted data to be erased from the system. All live data has to be available to be accessed. Sanitization needs to be efficient so that it doesn't consume all the resources of the system. The storage system needs to be usable while sanitization runs. So those are the 4 requirements that we have for our design. Just some quick introduction to remind us about deduplicated storage. So usually you have, to do deduplication, you have an index where you need to store your basically identifiers for the chunks or segments or chunks that you're using as unit of deduplication. You have your namespace, and you have in your namespace the files and some representation of the files. In here, I'm just listing each file as a list of fingerprints, which represents the data of that. Fingerprints it's a list of chunks. Each chunk is identified by a fingerprint, and a file is seen as a list of chunks. Those chunks, they are grouped together, and those chunks usually they are 8 kilobytes or whatever chunk size you have on average, and you group a bunch of them into a container and store them in a container, and the container set is organized as a log structure container set. The container set is managed as a log structure. So the main challenge here is in big systems, you may have hundreds of billions of chunks, and then how do you manage those references so that you can do sanitization? That's one of the big challenge that you have to actually carry out sanitization efficiently. So we have looked at a few techniques for that, so you can think of it. The trivial way of doing it is storing all the fingerprints in memory. But if you are using, let's say, 20 bytes fingerprint or whatever that size is, let's say 20 byte fingerprints to identify each chunk, you would need 160 bits per chunk, at least in memory, to be able to do the sanitization of the system, and that's a lot of space. So in this graph, if you look at the number of chunks on the x-axis and the memory requirements in the y-axis, you will see that the Bloom filter, the reference counts would require this much. This is log scale in both sides, 160 bits per chunk. We have used a Bloom filter as a suggestion here where, let's say that you're considering a false positive rate of 1 out of a million. For that, you would need 28.76 bits per chunk. One problem with that approach is that false positives may void your sanitization process, because if you have a false positive, you could actually leave something behind. So that's not actually an option for sanitization. So you need something that's collision-free or doesn't leave anything behind. Then you have the best solution would be if you were able to keep 1 bit per chunk in memory. That would give you the best memory requirements. And one that we find to be a very good trade-off is the perfect hash. If you know the set of fingerprints that you're working with, perfect hash is a very good data structure for that, and we can get as low as 2.54 bits per fingerprint or per chunk. So perfect hashing. For those that don't know what a perfect hashing is a very simple data structure where you have a static key set or key space, and you want to map that key space without collisions to, let's say, a perfect hash vector or a bit vector here. I'm using perfect hash vector because I was using bit vector for another reason before. So we call this data structure perfect hash vector, and for every perfect hash function, you need some bits to describe it and to store it, and you also need the entries that you're going to store your bits. So basically, in the end, your perfect hash vector memory requirements is the space for the perfect hash function plus the perfect hash vector, which basically is the range of your function. In a big system, we may have hundreds of billions of fingerprints, so we need to somehow, if you try to process this everything in memory at once, you're going to run out of memory, or you're going to have to partition your data somehow. So the index in our system is organized, it's bucketized, so we bucketize the fingerprints into the index, and we leverage that to build a perfect hash function by bucketizing it further, or grouping index buckets together into perfect hash buckets, and then we build a perfect hash function for each of those buckets. And this mapping is based only on the fingerprint, so it's a random mapping, and then those buckets are variable size, and because of that, you need an offset table in memory to get access to each chunk, to each perfect hash bucket or index bucket. The grouping is done in such a way that the average bucket size is 16K fingerprints. We have tried different values like 4, 8, 32, 64, and more details you can find in the paper. But this has shown to be the best trade-off in terms of memory utilization and time to construct the perfect hash and data structure. So that's what we use. And then now that we have given the basic idea of how we manage the chunk references in the system, we're going to get to our sanitization process, which is a 5-step process. And you can think of it as a mark and sweep algorithm as well. So basically, it's a 5-step and an implementation of a mark and sweep approach. In the very first step, we are trying to find the key space to build the perfect hash function, which is called merge phase. And then we have a cache of the we have an e-memory cache of the index, which has some fingerprints that we need to send to this before we actually get a frozen image of the system. So we merge that in-memory version of the index or buffer of the index to disk. And we also take a checkpoint of the file system, which are called consistency point 0 here. And the checkpoint basically means that you have a way to control the range of containers that at that point in time, or all the fingerprints that you have in your index will be within those containers. That's what we want from the checkpoint. And then the second step is called analysis phase, where we build the perfect hash function. And we use some algorithms that we have designed in the past, and they are very efficient, linear to build, and a constant time to access each fingerprint. So what we do, we walk the index now, which has all the fingerprints or the key space for my references in the system. And then we build a perfect hash vector data structure. Actually, we build multiple of them in parallel because we are bucketizing, so we can create multiple of them in parallel. And we also record which range of containers the data structure is actually covering. I will explain why we need that later on. So the third step is, so far we've done, we have created the perfect hash vector data structure. We now have an in-memory data structure. It fits in memory because of the compactness of the perfect hash data structure. That we can actually go and enumerate all the files in the file system and mark the reference that are there in the system or live in the system. So that's what the enumeration phase does. Then the fourth step is the sweep phase or the copy phase, which we go, and for each container that has at least one dead reference in it, we go and copy it forward into new containers. And the last step is zero out all the free blocks in the system and affected areas like swap and vrun and any areas that we might think that may be affected by the classified message incident. So this process is very simple, and it works pretty well in practice. If you freeze your file system, by freeze I mean you stop accepting writes while doing this. If you have writes coming in, your file system is not reading only anymore, and that's the fourth requirement. We want the file system to be available for writes and reads during the sanitization process, so you need to handle some problems because of deduplication. The very first one is, let's say that you have a chunk that's dead at the point that you do the enumeration, and now you are at the point that you're doing the copy, and some new file that's coming in has resurrected some old segments that were dead at the point you went through enumeration. So that's what we call resurrection problem. We need to handle that. So the second problem is that until you have your perfect hash data structure built, you don't have a place to go and mark bits as live in memory. So that happens only after analysis phase. So we need to address those two issues to support the read-write mode. So handling resurrections is basically done by having a mechanism with the deduplication engine. So all the incoming chunks, fingerprint chunk data, they are deduplicated. And after deduplication, the duplication engine notifies the sanitization process about each fingerprint and container ID that has been deduplicated. With that, you can check the container ID against the range that your perfect hash data structure is covering. And if that falls into that range, you can safely go and flip your bits in the data structure. If you don't have that, and you still go and flip the bits, you may end up with false positives anyway, because a perfect hash function, as I said, is a static data structure for the key space it was built for. So you have to have a way to avoid that. So the second problem, the way we handle it is, let's say that we have taken the first consistency point or the checkpoint of the file system. So we go and take a second consistency point. And when we take this consistency point, this is not an atomic operation. You may have multiple files being written to in your file system, and you need to flush each one of them out before the consistency point is taken. And because of that, by the time you're taking your consistency point, one file may have had some data written to it, and it's being synced to disk, and your consistency point is not capturing that, okay? So because of this problem, you need to take a second consistency point so that you make sure that all the references in your system are covered. But before taking the second consistency point, you need to turn on the notification mechanism so that you're guarded against resurrections from that point onward. So you first set up your notification mechanism, and then you take your second consistency point. And then after taking the second consistency point, as you can see here in red or reddish, there are two files that were modified as compared to CP0, okay? And then, based on those two files that were modified, we now do the enumeration in two steps. The very first step is to enumerate the difference between this consistency point 0 and consistency point 1, which basically correspond to file 1 and file n in this picture. And then we take all the fingerprints in those files, and we do index lookups for every fingerprint in that set. But this set's a small set because it covers a small window when you were building your perfect hash function as compared to your entire file system. And then we can afford for that small set to do index lookups, which basically corresponds to random disk IOs at that point in time because the index is huge. And then once you do that, you get to find out the container ID associated to each fingerprint, and then you can go to your perfect hash data structure and either flip the bits or just drop it if the container ID is not in the range. Then the second step of the enumeration is enumerate your consistency point 0, but because you took the consistency point 0 at the beginning, so you are guaranteed that your perfect hash function will cover every single fingerprint in that consistency point, and you don't need to do any index lookups at that point in time. You don't need to spend any random IOs. So that's how you can support the writes while running this. So we've done some analysis to evaluate this approach, and for that we have run the experiments on a 16-core machine, 2.53 gigahertz, 8 megabyte, 6 RAID groups. The total usable capacity was about 130 terabytes and 72 gigabytes of RAM. And we use a synthetic tool that is built in-house that mimics backup workload, which was built based on our prior experience on backup workloads. So that's a tool that we use to benchmark our systems internal. And then we did 3 sets of experiments. The very first one was to kind of lay down a baseline for the other ones. And in this one, we consider no deduplication. Just see how it performs on a system without any deduplication. But even though we don't have deduplication, we still have what we call compression, local compression in your system, which basically you apply a gzip algorithm, well, zip algorithm to compress data. And on top of what you write, you get the local compression for each segment. So in this, no deduplication is only no deduplication, but we still have the compression mechanism turned on. So in this case, we were able to get, so in these experiments, we wrote the entire file system, delete the entire file system from anywhere from I think 10 terabytes to 70 terabytes. And then after and each point corresponds to writing everything, deleting everything. It's only to see how sanitization would perform in that case. And in this case, the enumeration phase is pretty fast because you don't have anything to enumerate because the entire file system was deleted, okay? And in that scenario, we can do around 7031 megabytes per second as sanitization throughput. So if you now plug in the deduplication on top of it, which is the second set of experiments that we've done, and in this case, we did a single file system of 140 terabyte, and then we deleted portions of this file system, anywhere from 0 to 140 terabytes. So I always fixed the size at 140 terabytes, and then we were deleting chunks of that and then sanitizing. And here, the deduplication factor was about 7x. The deduplication factor, we tuned the tool to generate data that was about 7x of deduplication, the deduplication factor. And with these experiments, what we would expect is to get a boost in the performance of about 7x because you have deduplication that is increasing your logical space, and we expect to have 7x, which is the deduplication factor. And then we get 5.06 gigabytes per second, which basically corresponds to around so basically the deduplication factor was about 7.38x to be more precise. And we got a speed up factor of about 7.1x, which is pretty much says that we are able to scale this process according to the deduplication factor. So the third set of experiments that we've done was to benchmark this with ingests going on at the same time, okay? So if you remember, the enumeration phase now has 2 steps. The very first step, we will carry out a bunch of random IOs, and those, we want to restrict that interval to be as small as possible so that the amount of fingerprints that we need to do random IOs are very limited. And in this case, after doing these experiments, we did it with deduplication and without deduplication. If I have deduplication on, then the same factor, 7.38x, we were able to get 70x of the peak throughput of the system. So if you have no sanitization going on, that's the peak throughput. And with sanitization going on, we were getting 70x of the peak throughput. And sanitization itself runs at 59% of its peak throughput when ingest is not going on, okay? And the reason we can get both of them above 50%, when the 2 loads are going on, we throttle the system such a way that we partition the resource 50% to sanitization, 50% to ingest. But if ingest is not, and the resource to us is basically CPU cycles and IOs. So if ingest is not using IOs of the system, then sanitization is allowed to use as much as it wants, and vice versa. So the reason we can get both of them beyond 50% is because when you have deduplication, data ingest is actually CPU intensive rather than IO intensive. And then it's spending more CPU than IOs. And sanitization is actually the opposite. It's more IO intensive rather than CPU intensive. And that's why you can get the best, the leverage on both sides. So if you have concurrent data ingest and no deduplication, then now your ingest is also IO intensive because there's no deduplication going on. But it is also CPU intensive because we're doing compression and fingerprinting and everything. But sanitization is only IO intensive. In that sense, data ingest can still go at 70% of its peak throughput, and sanitization now goes at 45% because of the fact that ingest is now consuming more I/O bandwidth. So to conclude this, sanitization is a critical feature for security matters, and you cannot sell usually a storage system without it if you're trying, if the customer needs you to comply with DoD guidelines or NIST guidelines. We have proposed a process to carry out bulk sanitization of a storage system rather than devices, and to represent the chunk reference, we use perfect hashing, which is a good trade-off in terms of the amount of memory you need to use, and you can actually afford to fit everything in memory for a big system. We have nearly linear performance as the storage grows, and effective throughput multiplying with the deduplication factor. And one thing that you can think of you can think of this process as a garbage collector for the duplicated storage system. You can think of it like that as well. Although it's not optimized for that, because in sanitization, if a block or container has a single dead segment in it, you have to copy it into a new block and sanitize the block that you're freeing. So it's just one thing that I want to point out. If you want to use it for garbage collector, you need to be more careful. So with that, I'll open for questions. Thank you.
Dave Anderson, Seagate. Just as a point of information, the latest revision of this document explicitly recognizes cryptographic data sanitization.
Okay, thank you. This changed every year, by the way. I've seen it changing in 4 years at least 2 or 3 times.
Shen Kwong, Microsoft Research. I have a clarification question. So for the deduplication system itself, do you have to hold all the fingerprints for deduplication purpose in memory in the first place?
We actually, so if you look at the HP session, I think it's tomorrow, or yeah, I think it's tomorrow. They describe similar techniques that you can do to not have to hold everything in memory. Yeah.
And in terms of the second question, in terms of the memory efficient perfect hashing data structure, have you looked at other solutions out there? For example, there's this called a suite from CMU Group, which also claims to be very memory efficient.
So the perfect hash, the main advantage of it is that you can throw away your keys, right? So you have 20-byte fingerprints. As long as you freeze your key space and you have a way to control your operations so that you know that this fingerprint is coming from the set that I used to create this for, you can throw away your fingerprints, right? And then you only have a payload of 2 bits, 2.5, 2.6. I haven't seen any other technique that can do better than that.
Let's thank our speaker again.
Yeah, thank you.